Welcome to the world of industrial automation, everyone. Today, I will guide you into the world of industrial automation. We will explore intelligent control technologies within this field, especially the principles of PLC control technology. Exploring intelligent control technology. In today's industrial production, automation technology is applied everywhere. Intelligent control technology, as an important branch of automation, has greatly promoted efficient, precise, and intelligent industrial production. Through intelligent control technology, we can achieve precise control and optimization of complex production processes. This improves production efficiency and reduces production costs. At the same time, it ensures stable product quality. Unlocking PLC control technology, PLC, that is, Programmable Logic Controller, is one of the core devices in modern industrial automation. It features high reliability, strong anti-interference capability, and simple programming. It is widely used in various industrial control applications. Today, we will focus on the design and simulation of a conveyor forward and reverse control system based on the S7-1200 PLC. To further explore the essence of PLC control technology. Module 2, Basic Instructions and Applications of the S7-1200 PLC. In this module, we will study the basic instructions and applications of the S7-1200 PLC through a specific task, the design and simulation of a conveyor forward and reverse control system. We will master the practical application of these instructions. This task involves key concepts such as counters and forward or reverse control logic. Through detailed analysis and design procedures, you will gain a deeper understanding of the important role of these instructions in PLC control. 1. Task description. Our task is to design a PLC-based conveyor forward and reverse control system. This system must meet the following requirements. First, use the forward, reverse, and stop push buttons to control the conveyor direction. Second, use a counter to record the number of reciprocating movements of the conveyor. Third, set a maximum cycle count with an automatic stop function. Fourth, provide overload protection and an emergency stop function. The specific control requirements are as follows. After pressing the start button, the motor runs forward. After running forward for 5 minutes, it stops for 3 minutes. Then it starts reverse rotation. After running in reverse for 5 minutes, it stops for 5 minutes, then runs forward again. After repeating this cycle 5 times, the system stops. If the stop button is pressed, no matter which state the motor is in, forward, reverse, or stopped, the motor must stop running. The cyclic operation is terminated. The motor must also have an overload protection function. 2. Task objectives. Through this task, we aim to achieve the following objectives. Knowledge objectives: master the operating characteristics of PLC counters CTU, CTD, and CTUD. Understand the electrical interlocking principle of motor forward and reverse rotation. Become familiar with safety regulations in positioning control. Skill objectives: be able to design ladder programs for forward and reverse control. Be able to configure counter parameters to realize cyclic control. Be able to verify the effectiveness of interlocking logic through simulation. Develop the ability to design overload protection circuits. Quality objectives. First, master the debugging methods of counters in simulation software such as TIA Portal and Factory I/O. Second, understand the differences in technical response between simulation environments and real hardware such as signal jitter and noise interference. Counters. In PLC programming, counter instructions are very important tools. The S7-1200 PLC provides 3 types of counters: count-up counter, CTU, countdown counter, CTD, and up or down counter, CTUD. They are software counters. Their maximum counting speed is limited by the execution rate of the OB in which they are called. If a higher counting speed is required, the high-speed counters integrated in the CPU can be used. The working principle of counters is as follows. 2. Count-up input. When SU changes from 0 to 1, the count value, CV, increases by 1. CD, countdown input. When CD changes from 0 to 1, the count value, CV, decreases by 1. R, reset input. When R is 1, the counter is reset and CV is cleared to 0. The counter output Q becomes 0. When calling a counter instruction, a background data block must be generated to store the counter data. Counter parameters. The parameter configuration of a counter includes the preset value, PV, and the current value, CV. When CV reaches PV, the counter output Q becomes 1, indicating that counting is completed. By properly configuring the counter parameters, accurate counting of the conveyor reciprocating cycles can be achieved. Count up counter. When Q changes from 0 to 1, CV increases by 1. When CV equals PV, Q outputs 1. After that, when CU changes from 0 to 1, Q remains at 1. CV continues to increase by 1 until it reaches the maximum value of the specified integer data type. At any time, as long as R is 1, Q outputs 0 and CV immediately stops counting and returns to 0. Countdown counter. When CD changes from 0 to 1, CV decreases by 1. When CV equals 0, Q outputs 1. After that, when CU changes from 0 to 1, Q remains at 1 and CV continues to decrease by 1 until it reaches the minimum value of the specified integer data type. As long as LD is 1, Q outputs 0 and CV immediately stops counting and returns to the PV value. Up or down counter. When Q changes from 0 to 1, CV increases by 1. When CD changes from 0 to 1, CV decreases by 1. When CV is greater than or equal to PV, QU outputs 1. When CV is less than PV, QU outputs 0. When CV is less than or equal to 0, QD outputs 1. When CV is greater than 0, QD outputs 0. The upper and lower limits of CV depend on the maximum and minimum values of the specified integer data type. As long as R is 1, QD outputs 1 and CV immediately stops counting and returns to 0. As long as LD is 1, QU outputs 1 and CV immediately stops counting and returns to the PV value. There are 3 ways to create S7 1200 counters. First, drag the function block instruction directly into a block. The background data block of the counter is automatically generated. This block is located under System Blocks and GT Program Resources. Second, drag the function block instruction directly into an FB block to generate multiple background instances. Third, drag the function block instruction directly into FB or FC blocks to generate parameter instances. Possible reasons why the counter does not count. First, the counter input bits, CU, CD, must have a signal level transition. Only then will the counter count. If a constant signal is used as the input, counting will not start. Second, the counter background data block is reused. Working process. After pressing the start button, the motor runs forward. After running forward for 5 minutes, it stops for 3 minutes. Then it starts reverse rotation. After running in reverse for 5 minutes, it stops for 5 minutes, then runs forward again. After repeating this cycle 5 times, it stops. When the stop button is pressed, regardless of the motor state, forward, reverse, or stopped, the motor must stop running. I/O point assignment for the Conveyor Continuous Control System Design. PLC Program Development. Using TIA Portal software, according to the control requirements and the design program flow, we can complete the programming of the conveyor forward and reverse control system. The main steps are as follows. Create a new project. Double-click to open TIA Portal. Create a new project according to the wizard. Name the project Project 1 or another name. Enter a project description in the comment field. Enter developer information in the author field. Enter the project view. After creating the project, click Project View. The programming interface opens directly. Perform hardware configuration. In the TIA Portal project view, according to the selected PLC model and order number, add the PLC hardware. Set the IP addresses of the PLC and the local computer. Ensure they are in the same network segment. Configure the PLC CPU properties if necessary. Enable the PLC clock function. Configure the PLC properties. Enable the PLC clock function. Assign byte MB0, memory byte 0, as the clock memory. M0.5 is the 1-second pulse. Define PLC variables, name input and output signals, and create a PLC tag table. Variable names should be in English or Pinyin. This facilitates program development and debugging. Write the PLC program. According to the program design concept, the entire program can be divided into 6 program sections. Each section corresponds to one control task. The program logic includes start or hold or stop control, forward or reverse control, counter control, and so on. Simulation and debugging. After the program is completed, we can use simulation software for debugging. The simulation tool in TIA Portal is S7-PLC Sim. It allows us to simulate PLC program operation on a computer. This effectively verifies the correctness of the program design. The simulation steps are as follows. Right-click the project name at the top of the project tree. Select Properties. In the dialog box, select Protection. Check the checkbox Support simulation during block compilation. Click OK. Click the Compile button on the toolbar to compile. Click the Simulation button to start the simulation environment. Through simulation, we can simulate the operation of the conveyor. Check whether forward or reverse operation, counting, and automatic stop functions work correctly. At the same time, all abnormal conditions can be tested, such as emergency stop and overload protection. Task summary. Through this task, we have mastered the following key points. First, counter applications must be used with edge detection instructions to ensure counting accuracy. Second, during simulation, all abnormal operating conditions should be tested to ensure system reliability and safety. Third, in actual commissioning, disconnect the main circuit first for testing to prevent equipment damage caused by program errors. Fourth, by using counter instructions, we successfully completed the design and simulation of the conveyor forward and reverse control system. This provides valuable experience for practical applications in industrial automation.